Welcome to video lecture G5. This one is on orthogonal projections. I'll be your Sherpa Tom Roby. Here are the outline and objectives. We'll demonstrate the best approximation theorem that shows you that the orthogonal projection of a vector y onto a subspace W, we'll call that y hat, is the closest point in the subspace to y hat. Here's the picture of what we're going to see. Y projecting into y hat in the subspace W, and any other vector in W is going to be further away from y than y hat is. And then we'll analyze how our formula for the projection simplifies when we have an orthonormal basis for W. And then we'll rewrite that in terms of orthogonal matrices in a nice way. So here's the first thing, is to recall that we already proved and looked at carefully this formula for the projection onto a subspace W of any vector y. And the formula is just given as this ratio of dot products. If you want, you can think about the denominators as being the length squared of those vectors. But you just take y dotted with u1 and divide it by the length of u1 squared. And that's the amount that it projects, goes in the u1 direction, and so on for each of the different vectors. This is assuming that you have an orthonormal or an orthogonal basis. It doesn't have to be orthonormal for this formula to hold, but it has to be an orthogonal basis. Okay? And so here's the best approximation theorem. If W is a subspace of r to the n, and y is any vector in r to the n, then we'll set y hat to be this projection. So here's the vector y. Here's its projection. I guess I should label this subspace as W. And then the claim I'm making is that if I look at this distance from y hat to y, that's really just the length of this vector z, the orthogonal complement, which is y hat minus y, that distance is the smallest possible. That, in other words, if I take any other v here in W and I compare that blue distance to this orange distance, your colors may vary, then this is longer than that. Okay? And the proof of it isn't hard at all if you just, in fact, just to get a sense of the picture, we know that this is a right angle. And if we just draw this vector, if we look at this vector here, maybe I'll give this a different color. Let's see, I can't use blue. All right, so maybe I'll look at this vector. Then this, by the Pythagorean theorem, this blue vector is going to have length equal to the sum of the squares of the length of this, and that means it has to be bigger. But let me do that carefully for you right now. So here's the proof, right? If I think about y minus v, right? So that's this vector here, y minus v. So let's see. That's the blue vector. So this is the vector y minus v. That's equal to y minus y hat, this vector, plus y hat minus v hat. Okay, so that vector there is y hat minus v hat, or minus v. Right? V is just an ordinary vector. This is the projection. Okay? Now, because these two vectors are orthogonal, right, just because of the orthogonal projection, what we end up getting is that the norm of y minus v squared, so this blue length here, squared is equal to this length squared plus that length squared. And now that means that this length has to be strictly bigger than that length, right? And that's what this theorem is saying. Okay, so that's basically the whole proof of the best approximation theorem. But it's really useful to know when something is a best approximation, because in an upcoming lecture we're going to be talking about are called least square solutions, where we need to know, where we want to find the best approximate solution to a linear system that doesn't have an exact solution. So it's if it's inconsistent, but we still need to do our best guess. All right, so let's take a look at an example here. So suppose that W is the span of those two vectors. So you should think about, somehow you know that that W is the span of two vectors like that here. In this case, they're 3, -1, 2, and 1, 1, 1. And suppose y the vector y, which is not in the span of these, as you can check, because this system would be inconsistent, is 6, 4, negative 7. Okay? Well, then what's y hat? Well, so first of all, let's double check. Is this an orthogonal basis? Take the inner product. You get 3 minus 1 minus 2 is 0. Good, so they're orthogonal. And so now you just apply this formula and you say, all right, 3, negative 1. So I want to take y and dot it with the first vector, and then divide it by the length of that first vector. So I get 18 minus 4 plus 14 is 28. And then I divide it by the length of that vector squared, which is the sum of the squares of these things, which is 9 plus 1 is 10 plus 2 is 14. So I get 28 over 14 times that vector, 3, negative 1, negative 2. And now I do the same thing here, and I take the inner product of this with 1, 1, 1. That's much easier. I get 10 minus 7 is 3. I divide it by the length of this vector, so I get 3 over 3 times 1, 1, 1. And now I just add those. So I have to take 2 times this vector plus that vector. So 2 times 3 plus 1 is 7, and so on. So you end up with 7 minus 1, 3. And so 7 minus 1, 3 is this vector here, this y hat vector. 6, 4, negative 7 is that vector. And we've written this projection now. So this formula is saying that, I mean, it gave me the formula for this, but also I can think, if I'm thinking in terms of this orthogonal basis, that it's 2 of these plus 1 of those. Okay? So that's the... Then the other thing that we might want to do is to say, well, what is this distance of, between y and y hat? And so so then we need to actually do a little bit more computation, right? So in this particular case, let's see. Y minus y hat is equal to, okay, so 6 minus 7, 4 minus minus 1, minus 7 minus minus 3. And let's see, if I did that right, I get negative 1, 5, and negative 4. And so the norm of that squared is, well, negative 1 squared plus 5 squared plus negative 4 squared. And that's equal to, you got it, the answer to life, the universe, and everything, 42. OK, so then the distance, if I wanted to actually compute what the smallest distance is, the smallest distance would be the square root of 42. OK, so y minus y hat is equal to the square root of 42. OK, so now let's see what happens when we project onto an orthonormal basis. So first of all, we've got the same formula, but if our basis is orthonormal, then all of these green denominators vanish, right? Because they just become 1. I mean, they don't vanish in the sense of being 0. They vanish in the sense that they become 1. And so you just get this simplified formula for the projection of the vector y onto w, which is just y dot u1 times u1 plus dot 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 plus y dot up times up. Right? So each of these things is so this is a list of scalars that I'm a linear combination of the use of i's that I'm getting, and because this is an orthonormal basis for w, of course this vector is in w. Right? But here I claim I have a simpler way to write it just in terms of the matrices. I can kind of collapse all of these things into a single matrix computation. So if I let U be the n by p matrix of these column vectors for the orthonormal basis, then I can compute this projection just as U times U transpose times the vector for all vectors in R to the n. Okay, and this is really just something computational, but it's worth understanding because it's not too hard to see. So think about what U transpose means. Okay, so U transpose in this situation is going to be, if I'm thinking about this as being columns, then I want to think about it as being rows. So I think about it as being a list of rows, U1, U2, UP. Okay? And so these are, each of these is a length n row, and so now U transpose, therefore, is a matrix which is a P by n matrix. Okay? Now, if I take that and I multiply that matrix by y, what am I doing? Well, if I multiply it by y, then I'm multiplying it by y1 through yn. That makes sense, right? Because each of these is a length n vector, and so I'm taking the inner product of that. And what do I get? Well, I just get u1 dotted with y, right? Is the thing that for the first entry, because I just take each of these things, dot it with this, and so I end up with u1 dotted with y is the top entry, and u2 dotted with y is the second entry, and finally up, I keep making these not quite long enough, up dotted with y is the bottom one. All right, and so then this is a this is an p by n by 1, so I end up with a p by 1 matrix, which is what I should get. So this is n by 1, so therefore this is p by 1. All right, so that's good. So this is just a vector of length p, a vector in r to the p. And now what happens when I apply u to that? So I just applied u transpose. So I guess I should really say that this is u transpose y is equal to that. And so therefore, u transpose y is equal to, well, now I take this list of columns, u1 dot 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 up, and I multiply them by this thing up here. So this thing up here is a matrix of scalars, and now I want to think about matrix vector multiplication as just being taking this linear combination of these guys, and so I just end up getting this linear combination u1 dot y times the vector u1 plus dot 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 plus up dot y times the vector up, right? And that's the formula I have up there. Okay, so it's easy to see that this is just a condensed way of writing the formula that we've come to know and love. And now let's just ask us, so that was my reminder of what the proof should look like. And so first of all, let's ask a couple simple questions. Why? We must have p less than or equal to n here. Why? Well, for one thing, W is a subspace of r to the n. So the dimension of W needs to be less than or equal to r to the n. Or if you were thinking in terms of these vectors, you can say, well, I've got p vectors, they're bases, so they're linearly independent, and they're vectors in Rn, and you can't have more than n vectors in r to the n being linearly independent. That's really the same kind of dimensionality argument. Okay, so this matrix here, if p is strictly less than n, it'll be rectangular. And now, here's another interesting question. Let's think about U transpose U versus UU transpose, because here we have UU transpose. So U transpose U, as you may recall, U transpose U for a matrix with orthonormal columns is actually equal to the P by P identity matrix. And that's really just equivalent to saying that when you take UI dot UJ, you get 0 if I is not equal to j, and 1 if I is equal to j, right? And that's just how the identity matrix is defined. But in this situation, if you take U transpose U, then you're taking, what was it, a P by N matrix. Right, this is P by N times N by P, so you get a P by P matrix. But if you go the other way around, then you're taking N by P by N, and you're getting an N by N matrix. Okay? So what this matrix is saying is that that matrix is actually the projection matrix. And one thing we know about projecting, when you project something onto a subspace, if you started with something in the subspace, it still stays the same. You don't actually move it at all. Okay? So what that means about the matrix UU transpose, right? Since this is equal to projection matrix, what will it look like? Well, if you think about your basis, it's often useful to do this. If you think about, in terms of the basis U1, U2 dot 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 UP, you've got this whole chunk of the matrix where anything that can be written in just in terms of this basis alone so if you think about U1, that's in the subspace, so it's just fixed. So that means that U1 just goes to U1, 0, 0, 0. U2 just goes to 0, 1. 0 UP will go to 0, 0, dot, 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 1. So in other words, what I've got up in this corner is a P by P identity matrix. And now if you want to think about what happens in the rest of it, well, so anything that's in UP, this all has to be 0, right? Because you don't go outside of UP for things that are in UP. Now for things that are outside of UP, when you project onto them, you get things in UP, but you don't get anything anywhere else. So what that means is that I can have anything, funny things going on in this corner of the matrix, but it's actually still 0 in that corner of the matrix. Okay, because when I project, I won't get anything outside of my subspace W, and the rest of the basis here is for things that are outside of W. If I want, I could take an orthonormal basis or an orthogonal basis for all of R to the n and finish this basis out. But so that's what the form of the matrix looks like. And it's sometimes useful to think about it in this more concrete way. So I think that's it for video lecture G5. Thank you very much for your kind attention.